Yeah, okay, everyone. We'll get started. Yes. Okay, so last lecture, it's crazy. It's exciting that, we're already here. We're already at this point. Yeah, and let's cover what we're going to cover today. Oh, it's kind of weird. All right, whatever. Let me share the screen. Okay, so it's a fairly short lecture today, to the point where we can even kind of take the worksheet up, as we were kind of saying in the chat. That being said, I think I'm more or less effectively going to cover some of the worksheet problems in the process of actually, getting through the lecture. But there might be something, one or two things to cover by virtue of this. Now, for today, just to kind of give you a little bit of a heads up, we really want to tap into what I think we remember from linear algebra. And so I say this because, the first time I learned this subject, so today we're talking about internal direct products. The first time I learned this subject, I didn't have the linear algebra that I needed to really understand what this thing is. So once I understood that from a linear algebra viewpoint, it made things much easier. I'm going to at least try and motivate it from that viewpoint, and hopefully it helps. But if it doesn't help, whatever, it's not that big a deal. You can just basically ignore what I do. But I do want to motivate it from that viewpoint. So hopefully, we kind of remember how our linear algebra stuff went. And that will help us understand what's going on here. So last time, right, we talked about external direct products, right? Maybe even let's recall that, because these are going to be pretty related. So let's maybe say quickly, recall, right? We had external direct products. Right? And we would say something like G is equal to H plus K. And then the group operation here was, we do H1, K1 times H2, K2 is equal to, and we would just do that component wise, right? We would just say, oh, we're just we know the H's have a group operation. We know the K's have a group operation. We just, smush them together like that. And the H's and K's don't really see each other, right? They don't interact in any way, shape, or form. All the H's stay together and all the K's stay together. Okay, so that's just a really crash course in what our external direct product was. Okay, and so here, the H and K really don't have to be related to each other. They don't have to be related to G, at least not a priori. They kind of like get smushed together to become this new group G. So what we want to do in this lecture is go the other direction. So we want to say, let's suppose that you have a group. So our goal for this lecture is to go the other direction. Right? And we want to say, all right, if you have a group G to begin with, can I find subgroups that I can smush together in an appropriate way to give me back G, right? That's what we want to do. So given G, can we find H and K, let's say in G, such that G is the product. I'm going to put that in brackets or, in quotes for now, and then we'll explain what that means, such that G is the product of H and K. All right. Now, this is going to look different at first. Our first kind of exposure to this is going to seem really, really weird. And you're going to be like, how is this possibly the right definition? But it turns out it is. And I'll try and explain that and motivate why that's true as we go. Should I give you the definition first, or maybe I should recall some linear algebra? Did we say 224 was a prereq for this course? I don't really remember. Is that true? Has everyone taken like 224 or 240 or something like that? Some sort of linear algebra, right? I think so. Because if not, yeah, I think so. So unless there's any major objections, I'm going to kind of all assume that you've seen this. So does everyone remember how to do an internal, or even, an internal direct product of groups? We probably called it an internal direct sum when we did it in linear algebra. Does that ring any bells? It ends up being very important in like 224. I think you basically have to do it. Okay, well, hopefully this won't be too crazy then. Okay, so from linear algebra, suppose V is a vector space. is a vector space with subspaces U and W, right? So what we would say is we'd say that V is equal to U plus W. And here we have to be a little bit careful about notation. We say that V was the direct sum of U and W if two things happen. One, V was equal to U plus W. Right? And two, U intersect W was the zero vector. Right? And basically what this told us was the following. The first condition said, every element in V can be written as a sum of U and W, which was important, right? So everything can be decomposed into U plus W like that, right? And then the second thing, we guaranteed that that decomposition was unique. So the decomposition, or what I mean by that is if you took an arbitrary vector, wrote it as U plus W, then there was only one way to do that because U intersected W trivially. And hopefully when you were doing examples of this, you saw cases where if U and W didn't intersect trivially, it was actually possible to write it in a couple of different ways so that this was precisely the right condition. Does this ring any bells? Is this kind of like familiar? Right? So you could write V as U plus W, and then U and W intersected trivially, and that guaranteed uniqueness. Okay? And like I said, I'm certain this shows up in 224 because it has to be used a couple times there, depending on kind of what the curriculum is. Okay, so those are the things that are true for vector spaces. And I want you to keep in mind that in a vector space, for example, if you forget scalar multiplication, right, and you just look at the addition of vectors, that's a group. In fact, that's an abelian group, right? The vector space structure on Rn, if you throw away scalar multiplication, is an abelian group. So when I say all of these things, when I talk about a vector space, when I talk about subspaces U and W, I'm talking about a group and I'm talking about its subgroups, right? These are guaranteed things. We know that these things are true and the identity is the zero vector. Okay, so again, this is kind of just to help us place what I'm about to say into context. Because I think when you see this definition, if you don't have this linear algebra idea in mind, you're going to be like, well, what the hell is going on here? Okay, so here's the definition. And we would say, again, this in linear algebra, we'd say V is equal to U plus W. We'd say usually that's a direct sum. And again, that's the notation that we've used in this class for an external direct sum. I don't like that notation. And it might be a little bit confusing because, again, we're about to do internal direct sums. That's the notation in linear algebra that we use for internal direct sums. Just kind of keep those separate in your brain. All right, here's the definition for groups. So definition. So let's suppose G is a group, and H and K are normal subgroups of G. Okay, so this is immediately something that's a little bit different from vector spaces, just because we don't have to talk about some notion of normality. Vector spaces are abelian, so all subgroups are normal, right? But in this case, we're going to need normality, and I'm going to show you why later. So suppose G is a group and H and K are normal subgroups. If G is equal to HK and H intersect K is the identity, then we say that G is the internal direct product of H and K. And we write this as G equals H times K. Okay. So just a couple of points I want to make immediately. our notation in this class is actually backwards than I would use in real life. Okay, so in real life, I would use the internal direct product to denote that. I would use the O plus, right, the plus sign with a circle around it. And the external direct product, I would use the multiplication sign. But for whatever reason in this class, we've switched them. I think that, again, it's a little bit fuzzy kind of about what happens in real life. There's a notion here where these notations actually mean precise things like coproducts and products in a categorical sense. We're not going to worry about that in this class. It's a really cool thing if you ever want to get into homological algebra and category theory, but they actually mean strict things, right? So that's something to keep in mind there. But now the other thing that I want to do is let's compare this to the definition of an internal direct product that we have above of vector spaces, right? So what do we have? We have that V is equal to U plus W. Let me do the corresponding thing for groups. It would be G is equal to H times K, right? And again, here, this notation implicitly means we're using multiplicative notation for the group, right? We're saying we're doing H times K. But if G is abelian, this is effectively H plus K, right? Usually for an abelian group, we use an addition sign in order to, remind us that it's commutative. And in that case, if the group operation is addition, then this would look like H plus K, right? Which is exactly that thing that I underlined in yellow for vector spaces. So this is exactly the same condition, just now generalized for arbitrary groups, including potentially non-abelian multiplicative groups, right? The other thing is that, we wanted this uniqueness condition to still be true. U intersect W was equal to the 0 vector. That shows up here as well, right? That H intersect K is equal to the identity. They have to intersect, right? Every subgroup has the identity element, just like every subspace has the 0 element. So their intersection can't be empty, but it can be as trivial as possible by just intersecting in the trivial group, right? So those are the two conditions. The only one that, again, shows up and is a little bit weird is this, here, let me underline it in green, is this normality condition, right? And again, that doesn't show up in vector spaces simply because every subspace is normal in the underlying group structure, so it doesn't need to be said, right? It's like we were only working with normal groups, we wouldn't say this condition because it's just always true, right? We would always have normality. So it's exactly the same, word for word, exactly the same definition as what we had from linear algebra, just now more general, right? And can apply for non-abelian things as well. Okay, so does that make sense? Let me know if there are any questions. Hopefully that's settling in and isn't too crazy. So far, so good? Okay, so I'm going to do two examples here. I'll do an abelian example, and then I'll do a non-abelian example. And what we're going to see very, very quickly is that these things also look like external direct products, right? But and we'll kind of prove that later. So what I want to say as our first example is let's take Z6. Okay, so cyclic group, 6 elements, and there are two obvious subgroups of this thing. So I'm going to take H to be 0, 3, right? And K to be 0, 2, 4, right? Okay, so the group operation here again is addition, and you should convince yourself it's not too hard to just look at these two things and say, oh yeah, I can get every element of Z6 by adding something in H to something in K. So I'm going to say check. I don't want to say clearly, but check that Z6 is H plus K. And again, here I'm just going to use the plus sign. Again, normally we would usually use multiplication, but in this case, the abelian operation is addition. So I'm going to write it as H plus K here. But convince yourself you can get every element, right? You're like, okay, how do I get a 1 from this? Well, 1 is 3 plus 4, right? 2 is already in K. 3 is in H, 4 is in K. How do I get 5? Oh, it's 3 plus 2. And there you go. And now you've gotten every single element, right? So every single element is either in H or K or is a sum of an element from each of them. So it certainly adds to everything. And just by inspection, their only intersection is in the identity element of 0, right? And note that their intersection, H intersect K, is just equal to the 0 vector, right? Therefore, this must be an internal direct sum. Thus, Z6 is equal to H times K. Okay. And again, what this basically says, right? The whole point of this is that if you, actually, you know what, maybe, no, let me do another example and I'll show it up in a second. The entire point of this is effectively to say that Z6 can now be written uniquely. Every element of Z6 is uniquely an element of H plus an element of K, right? That's effectively what we're going for here. And again, you can look at it and you can convince yourself it's true. There's only one way of writing 5 as something in H plus K. It has to be 3 plus 2, right? There's no other way that you can do it. There's only one way of writing the number 4, right? It has to be 0 plus 4. That's the only way that you can do it, right? So that ends up being critical. Another kind of comment to note here, H is isomorphic to Z2, right? It's a group with 2 elements. There's only one of those things. K is isomorphic to Z3. Right? It's certainly cyclic. It has order 3. So H is Z2, K is Z3. And we know as an external direct product, the Z6 is Z2 cross Z3, right? And we know that Z6 is isomorphic to Z2 external direct product Z3, right? This is something that we did last time. ZP plus ZQ is isomorphic to ZPQ if and only if P and Q are coprime, right? 2 and 3 are certainly coprime, so we certainly get that it's isomorphic to Z3. So this is interesting. We said, look, Z6 can be written as this internal direct product. Those two things are isomorphic to its external direct product as well. So something here is seeming, like maybe these two things are related, right? Maybe internal direct products and external direct products are very, very similar. Okay, let me do another example. Okay, so let's do a non-abelian example. So let's say take D6, right? The dihedral group of the hexagon, right? It's the symmetries of the hexagon. So this is R and F such that the order of R is equal to 6. The order of F is equal to 2. And what is it again? It's F, R, F is equal to R inverse, right? So this is the presentation of D6. And there are a couple of, again, very natural subgroups that we can take. So let's say set H to be, what do I want here? I want the identity, symmetry, the one that doesn't do anything, and R cubed, and K to be, what do I want K to be? So I want it to be the identity, obviously, right? R squared, R to the 4, and then I want the flip, and then R squared F, R to the 4F, like this. Okay. Let me just double check. I put the F's on the right side, just so I don't get angry at myself later. R squared F, R to the 4F, perfect. Okay. All right. Now, again, so this one's a little bit trickier, right? D6 has 12 elements here, and certainly we agree, all right, if something's going to work, a group of order 2 and a group of order 6 seem like those are the right things to combine together. So immediately they intersect in the identity element, right? So I am going to deign to say clearly here, clearly H intersect K is the identity, right? It's the only thing in both groups. A little bit harder to check is that H times K is all of D6. So somewhat tougher. Excuse me, is that HK must be all of D6. On the other hand, you could say that's not too crazy. Their intersection is trivial. So we have this formula which tells us precisely how big what the cardinality of H times K is, right? And yeah, it's easy to convince yourself in that case that it's 12 and therefore it must be everything. Alternatively, you can actually go ahead and you can just check, right? There are 12 elements, you can write them all down, right? It's all the powers of R and then all the powers of R times F. And again, if you look at these two things, you say, oh yeah, I can generate everything that I want in that way, right? Like, how do I get just R? Oh, it's R cubed times R to the 4, right? That's equal to R. How do I get, R to the power of 5 times F? Oh, it's R cubed times R squared F, right? R to the 4 might be, F is a little bit tougher, but it can be done, right? It's not too bad. So, give that a shot, see if you can manage to put it together and just convince yourself that this is true. Okay, so once again, we get that there's this internal direct product between D6 and H cross K. D6 is isomorphic to H cross K. Okay, and moreover, so H is again, obviously Z2, right? It's a group of order 2. There's only one of them. And so as an aside here, let's say note H is isomorphic to Z2. Does anyone have a guess of what K is isomorphic to? Any guesses? It's a group of order 6, right? We've only got 3 of them. So what does it got to be? Any guesses? Because if we enumerate our groups of order 6, what do we got? We've got Z6, right? In fact, no, I guess we've only got 2 of them. We've got Z6 and we've got S3. And if this thing's not abelian, well, it's got to be S3. So it's pretty easy to check. This thing is isomorphic to S3, right? And in fact, if you want to explicitly construct that isomorphism, which again might be a great exercise for you to do, I'll write it down here so you can kind of check it later, but, convince yourself that this thing is isomorphic to S3. Let me write down the isomorphism for you. So what I want to do is I want to map K over to S3. So evidently, I'm going to take R squared to 1, 2, 3, right? You could take it to 1, 3, 2 if you want, but R squared has to map to a thing of order 3 because R squared obviously has order 3 in K, right? R squared, R to the 4, R to the 6 is the identity. So it has order 3. It has to be one of those 3 cycles. And then F, R squared F, and R to the 4F all have order 2. Those are exactly your transpositions. And it really doesn't matter which transpositions you map them to as long as you do it. Okay, and again, it's not hard to check that each of those things has order 2, right? You're really going to lean on this, right? On the F equals R inverse in order to be able to do that, but it's very easy to check. Like obviously F squared is the identity. Is R squared F equal to the identity? Yes, multiply it by itself and then just keep using that identity over and over and over again in order to show that everything cancels out and you get the identity. Okay, so that's not a hard exercise, but if you want to do it, check. This is in fact an isomorphism between K and S3. So this is cool, right? I think that this is really, really nice. Like look at D6 here. We're saying D6 is an internal direct product of Z2 and S3. Like that's really, really cool. Moreover, we're going to show in a little bit that there's a bijective correspondence, or in fact, an isomorphism between the internal and the external direct product. If we use that information right now and kind of think ahead, that's telling us that D6 is isomorphic to the external direct product of Z2 and S3, right? So I think that that's really, really cool. Just being able to see that those things are isomorphic, like that's not at all obvious, right? And I think it really lends some weight to like, what is an isomorphism? Oh, it's showing you these things are morally the same thing. Even though they might look a little bit different, they really are the same thing, right? Okay. Okay, so what I guess we should do is, let me say this. I actually realized this as we were writing this out. We didn't really explain, I kind of tried to justify it with this linear algebra approach, but we didn't really explain why we ask that this be true. For example, why do we say that this is an internal direct product if G is equal to HK and H intersect K is the identity, right? And again, the idea here is that we're saying you can write every element of G as a product of H and K, but more importantly, that when you do that, when you write G as H times K, that way of doing it is unique, right? There's only one way of doing it. So let's prove that really, really quickly. So theorem, and I want you to think about how we do this. So if G is equal to the internal direct product of H and K, right? So I'm not going to do, H and K are normal, they intersect trivially, yada, yada, yada. We know all of that's true when I write this notation down, right? We're guaranteed that that's true. If G is isomorphic to H cross K, then for all G in G, little g in big G, there exist unique, maybe let me put that in words. Let's not use symbol. There exists unique H in H and K in K such that G is equal to HK. Okay, so I think this is maybe missing from the notes. Like, I don't think that this theorem is kind of explicitly said, but this is the critical part about being an internal direct product, right? This is the entire point. Every element can be written as H times K, and that decomposition is unique, right? This is an existence uniqueness. We need to prove both exists and that it is unique, right? And again, this isn't that hard, right? This ends up actually being really, really easy. So proof. Well, at least the exists is really easy. The unique is a little bit more work, but it's not that much more work, right? So exists just follows because G is equal to HK, right? So let's say fix some G and G. Right, so since G is equal to HK, we know there is an H in H and K in K, that is an H, such that G is equal to HK. Okay, so that covers existence, right? Like that wasn't too hard. So what we need is uniqueness. So this one ends up being a little bit more work, right? So for uniqueness, let's suppose that we have an alternative decomposition, right? To show this is unique, suppose that we could also write, so I'm going to write HK is equal to G. So that's the one we kind of already have. And now I'm going to suppose that we could write it in a different way, right? So H hat, K hat, like that. Okay, so for some other H hat and K hat, presumably, but I'm going to show they actually have to be the same. So what I'm going to do now is I'm just going to put all the H's on one side. I'm going to put all the K's on the other. So let's say rewriting this, we get, okay, so again, I'm kind of ignoring the G in between. I'm just going to look at these two things, and I'm going to put all the H's on one side. So what am I going to get? I'm going to get H. Well, let's try and use the inverses as little as possible. I can't avoid it. H hat inverse is equal to, so I put that on the right, is equal to K hat K inverse, like that, right? So multiply both sides on the right by K inverse, multiply then both sides. Let me just double check here. Did I do something dumb? So on the right side by K inverse, that's going to be H is equal to H. Oh, I need to put the H hat on the left, don't I? Yeah, sorry. It doesn't make a difference. There we go. Right? Did I do that? Yeah, that's good, right? H hat should be on the left. So what we get is that this thing, H hat inverse H, is in both H and K. right? So the left-hand side is in H, the right-hand side is in K, but those things intersect trivially, right? I said the whole point of requiring that the intersection of H and K be trivial is to guarantee the uniqueness of this decomposition. And here's where we're getting it. So the left side is in H, the right-hand side is in K. That means both of these things have to be the identity. Thus, H hat inverse H is in H intersect K, which is the identity. So H hat is equal to H. And for exactly the same reason, K hat K inverse is also the identity. And similarly, K hat must be equal to K, right? So therefore the decomposition is unique. I've said no matter how you choose to write it, you have to use the same H and the same K, right? And this makes sense, right? This is what we want, that this should be true. Now, it's very reasonable at this point to say, did we use normality here though? Because it doesn't look like normality really showed up, right? I used the fact that G was equal to HK and the fact that their intersection was trivial, but did I really use normality? And I think it's fair to say at this point, no, but what I am going to show you where we are going to use normality is precisely when we show that the internal and external direct product are unique. Or maybe let me do it as a corollary. Okay, here, let's do this. And okay, here, let's take this as a proposition. No, this is a theorem. Let's say theorem. So again, let's suppose G is equal to the internal direct product of H and K. My claim then is that the H's and the K's commute with one another. Then for all i.e., right, H is in the center of K, K is in the center of G, yada, yada, yada. So that's a little bit clunky. Then for all H in H and K in K, we have KH equals HK. Okay, so they commute with each other. All right. So actually, I think you should try this yourself. Like if you've done the reading, I don't think this one is maybe too surprising. Let me give you, a couple minutes, let's say 3 minutes, to see if you can sort this one out for yourself. Note, again, I really haven't used normality, right? And based off of what I was just saying, this is probably where normality is going to come up. Now, the proof of this in a more general form is in the book. So if you really are desperate and want a hint, you could go look it up there. But give it a shot for yourself. Like I said, normality is the key here. And let's see, I'm going to give you 3 minutes. Let's see if you can come up with an answer. Okay, so give that a shot. Okay, so that was 3 minutes. Did anyone think they made any progress? I know 3 minutes probably doesn't seem like a terribly long time, unless you're the person sitting on the other end of this just screen waiting for it. No. So if you're interested in where G is equal to HK, sure. And then what did you do? Okay, sure. And what did you use to manipulate? Like, did you multiply it by like H inverse H, do something like that? Okay, yeah, sure. Let's do it that way. Okay. So again, there's a sort of a similar proof. Okay, no, that's all right. And then, yeah, I mean, if you kind of want to continue to do it on your own, then you can kind of ignore what we'll do, but let me do it your way, which is not how I did it, but like, I think that should totally work. So let's say fix some H in H and K in K, right? So we have HK is equal to HK H inverse H, right? Because so I just multiplied that right-hand side by the identity. Now, HK H inverse, this thing is in K. So this is going to be Yeah, how do we want to do it this way? So this is in K, but we don't know that it's equal to K, right? And that's kind of the issue here. So this is equal to maybe like K hat H for some K hat. But then I guess we could say, what if we tried to do this as well in the other direction? So if we did KH is KH K inverse K. Okay, so this one now is in H. So that would give us like some H hat K. I don't see, yeah, I mean, like in some sense, when I write that, yeah, so when I write HK, right, I automatically assume it's in G. No, this is the right idea. It's just, it might be a little bit hard to work with because it's hard to figure out what this K hat has to be, right? Like basically what we know kind of looking, ahead, we know that H and K should commute. So this element really should just be little k, not just in K, this actually should be little k, right? But the problem is that we kind of have to prove that H inverse is equal to little k. That's gonna, give us a little bit of trouble. So the other thing to keep in mind here, let me show you how I did it, and maybe that will help. This is a common thing that we do, especially in group theory. But so let's take HK, H inverse, K inverse, right? And if we can show that this is, remember, this is the commutator of H and K, right? Just as kind of a little aside, right? We defined this thing as being HK. So if we can show that this thing is the identity, then we're done, right? We will have gotten that H and K must commute. So it's this typical thing in mathematics where if you have an equal sign, you're trying to prove something about an equal sign, sometimes it's actually much easier to move everything onto one side of the equation, right? And then prove that that thing is equal to 0 or the identity or whatever the case might be, right? So that's kind of a common thing that we do. So in this case, if I want to prove that KH equals HK, let's put everything on one side of the equation and prove that that thing has to be the identity. And the benefit of this is you can already see the like HKH inverse or the KH inverse K inverse, right? Like the conjugates are already there, which is really going to be a big advantage when we want to use normality, right? Which is what I tried to hint that was sort of the thing that we wanted. So you can see this is almost the same setup as what you had, just slightly different. And I think this one might be a little bit easier to work with. So what I want to say is just using like associativity. So if we just do this as HK inverse K inverse, by normality, this thing is in K inverse, right? Since K is normal in G, HK H inverse is equal to K, right? So that's what I'm using. But K inverse, K big K times K inverse is just equal to K, right? And then if we do the other direction, so if we bracket this in a slightly different way, and we bracket it like this, so that will give us K H inverse K inverse. That's going to be an HH, which is just equal to H. And again, here, since we're using the fact that H is normal in G, so K H K inverse is equal to H, right? So what that means is this thing is in the intersection and therefore is it has to be equal to the identity. So HK, H inverse, K inverse. I realize my Ks are starting to look like Rs. And we're done. Okay. So that's sweet. That's awesome. And again, to some extent, we expect this to be true. And the reason why we expect this is because I keep hinting and alluding to this fact that this is going to be isomorphic to the external direct product. And again, if we think about the external direct product, we know that H and K don't really interact with one another, right? They do their own thing. All the H's hang out on one side of the, in the first element of the tuple. All the K's hang out in the second element of the tuple, and they don't really interact with each other. So when I take an internal direct product and H and K are somehow implicitly related to one another, what is the natural way of me saying all the H's hang out together, all the K's hang out together, and they don't really interact? it's precisely this commutativity statement, right? Because the H's and K's all commute with each other, I can take any product of H's and K's and move all the H's to one side and all the K's to the other side so that they're homogeneous and they just play with each other. They don't really see each other in any way, shape, or form, right? So this is precisely the correct notion of saying in the external direct product, H's and K's don't see each other, to saying in the internal direct product, they kind of don't see each other either, right? This is the correct thing to say here. Okay. Are there any questions about these two things? So these are kind of like the two critical things to keep in mind, right? If you're an internal direct product, every element can be written as a unique as H times K in a unique way, and those H and Ks really don't interact with each other because they commute. Obviously, they do have to, at the end of the day, you still have to multiply them together, but morally speaking, they kind of do their own things. Okay. Okay, so we basically have all the tools that we need now to prove that the internal and external direct products are isomorphic. And in fact, the isomorphism in some sense is the obvious thing that you would want it to be, right? So theorem, if H and K are groups, the internal direct product is isomorphic to the external direct product. Okay, and the great thing about this proof is it is the naive thing. The first thing that you want to try 100% works, right? And in some sense, mathematically, we might say that that's boring. On the other hand, as a student, you're like, yes, right? Like that's 100%. Like I don't want creativity. I just want the naive first thing that I should try should work, right? So if you wanted to show that these two things are isomorphic, what would you do? You'd set up an isomorphism, right? Or, you could try and do it using first isomorphism theorem or something, but these two things just are kind of intractable to work with and to relate to each other. So let's say define phi, and I'm going to take it from the external direct product, which remember is the set of tuples, right? H comma K. And I'm going to map it to the internal direct product. And the way I'm going to do this, the reason why I say the naive thing is what I'm going to do is just multiply the two elements together, right? So again, I'm kind of assuming here that there's this, maybe I should put my statement in here so that I have that G is isomorphic to both. Right? So again, when I write H and K are, internally related, there is this background group operation going on here, right? So that H times K makes sense. These aren't just two separate groups. They're being understood as being internal groups. And so that H times K makes sense. Okay. So there is some bigger ambient group hanging around in the background. So okay, what do we need to show? So we need to show three, or really just two things. We need to show that this is actually a homomorphism, right? It's not enough to be a bijective function. It has to be a homomorphism. And we need to show it's bijective. And if you want, you could break bijectivity into injectivity and surjectivity, which we will. Okay, so one, let's check. Is this a homomorphism? Okay, so let's do this. So let's compute phi h1 k1 times h2 k2, right? So we know that's going to be phi of h1 h2 k1 k2, and that's going to be, again, we're just going to multiply everything together, be consistent with my k's, k1 k2. Yes. And now what I'm going to do is, again, I know that H's and K's all commute with each other, right? So I can just switch H2 and K1. H1, K1, H2, K2, right? So since H and K commute. And that is exactly phi h1 k1 times phi h2 k2, right? So yeah, it is a homomorphism because that's exactly the property that we needed to be true, right? Okay, is it injective? Or let's say maybe first, is it surjective? And that one's trivial, right? Yes, trivially, okay? And again, if you don't quite see it, let's look back at the definition of phi. It's going to take an element in H and an element in K and map it to an element in HK. How would you prove that this is surjective? Choose an element on the right-hand side, call it H times K. Well, what maps to that? Clearly H comma K, right? So this is why I'm saying this one's trivial. There isn't anything to do. If you really want to write it out, sure, go ahead and do it. It's a one-liner. Choose an element on the right-hand side. There's an obvious thing which maps to it, right? And then finally, injectivity. And we've already done that already. Injectivity is precisely this uniqueness property, right? I'll write it out for you, but again, start thinking ahead of time. It's just precisely the injectivity property. Or sorry, it's precisely the uniqueness. Is phi injective? Injective. So yes, if phi h1 k1 is equal to phi h2 k2, so what does that mean? That means that h1 k1 must be equal to h2 k2. But again, everything in the internal direct product is unique. So the only way these two things are equal is if h1 is equal to h2 and k1 is equal to k2. Since the decomposition is unique. Right? There's only one way of writing each element in HK as something in H times something in K. i.e., what did we do? Thus, H1 K1 is H2 K2. And we're done, right? So we've proven it's a bijective homomorphism. It's an isomorphism, right? So we're done. Okay, anything crazy there? Well, let me see. Is there anything else I want to do? I guess there are a couple of things before I go on, but we are at that 2-hour mark, so maybe we should take a little bit of a break. So there are a couple of little things that I want to do. So I wanted to say, for example, how do we generalize this? So just like in linear algebra, we talked about how to write a vector space, not only as a decomposition of 2 subspaces, but potentially of n subspaces, or even perhaps infinitely many if you have an infinite dimensional vector space, and we should be able to do that with groups as well, right? So I want to do that. And then there are a couple little exercises that I want to do. And then we can start to do the handout. That being said, though, I think the handout, let me just pull up the handout really, really quickly. I think the handout is like really, really straightforward. Where is it? 13 worksheet. Okay, question 1 isn't too bad. Question 2 and 3 are intimately related on the worksheet. So we'll kind of get into that, all right? But why don't we take a 10-minute break right now? We'll come back in 10 minutes and we'll do the couple more things that I want to do. Shouldn't take, I hope, more than 15, 20 minutes or so. And then we'll do a couple of the worksheet problems and we'll see how that works out. And then we're done. And then we're done the course. So that'll be good. Okay, so let's take 10 minutes. And again, for those of you, I know how many people have filled out. I obviously don't know who filled out the course evaluations, but I know how many did. And I know that there are more people here now than have filled out the evaluation. So for those of you who have not filled out that course evaluation, please go do that during this break. I have 2:02, let's say 2:03 by my clock. So we'll come back at 2:13 and we'll finish it off when I get back. Okay, so let's do that. Everyone, let's take 10. And I'll see you back here in 10 minutes. Okay, so it's been 10 minutes. We can carry on here. Let's see, what did I want to do? What did I want? Oh yeah, so I said I was going to tell you about how we generalize the notion of an internal direct product to, let's say finitely many subgroups. Oh, sorry if that's a little loud. Okay, so the way we generalize this is as follows. So definition. So let's say if G, why do I feel like my writing is skinnier? If G is a group and H1 ... Hn are subgroups, such that one, each of the subgroups is normal, right? Again, naturally that has to be true. So Hi is normal in G. 2, G is equal to the product of all of them, right? So again, this says every element can be written as a product of H1, H2, all the way through Hn. And then 3, H1, H2, ... Hi intersect Hi plus 1 is empty for I equals 1 to n minus 1. Okay, and again, this is going to give us the uniqueness condition. So if this is true, then we say G is this internal direct product of H1 through Hn. Like so, okay? And once again, as an immediate result of this, you can check it for yourself. So check if G is H1 cross H2 cross ... cross Hn, then every element of G can be uniquely, that's important, uniquely written as G is equal to H1, H2 ... Hn with Hi in big Hi, right? All right, and so this is the correct thing. Again, I think 1 and 2 maybe aren't surprising. 3, a little bit unorthodox, but not a big deal. Okay, and so again, you can generalize this. Yeah, I can't think of too many like good examples of where we might do something like this, but it's nice to know that theoretically you could do it. Let's see, is there anything I want to do? Okay. So let's say then, here's a little exercise we can try. So exercise. Okay, so suppose, and again, I'm just going to go back to 2. I wanted to show you how to do it in general, but most of what we do is just going to be 2 direct, 2 subgroups in our product. So suppose G is isomorphic, or G is equal to H times K, and N is normal in H. Show that N is normal in G. Okay, so we've got an internal direct product of G with H cross K. We're told that N is normal in H, so that N is normal in G. It occurs to me we could probably cheat because I'm pretty sure that we proved this exact result for external direct products. And we know the internal is isomorphic to the external, so we could just cheat that way. But let's say don't do that. Don't use that the internal and external direct products are isomorphic. Just try and do this directly from the application of the internal or the definition of the internal direct product and see if you can come up with anything for it. Okay, so I'm going to give us, this has nothing to do with the, H1 through Hn. So I'm going to give us a couple of minutes to try this, see what you can come up with. For the most part, you just apply the definition and you get down to the very end. And then when you're at the very end, you just need to make a little argument. But most of this is just writing out what the definition is. Okay, so again, I'm going to give you, let's say 3 minutes. Let's see, maybe 4 minutes. Let's see where we get on that. and then we'll take it up. Okay, so let's give this a shot. Hopefully managed to make some progress on it. Oh, is my pen dying? Prove, or let's say solution. Solution. Pen, what are you doing? Okay. So let's just set it up. Like, let's not worry about doing anything. What do we need to show? So we need to show that for any G and G and little n in n, G and G inverse is in n, right? So we need to show, okay, this is not going well. Let me just fix my pen here because it is acting up. All right, hopefully this fixes it. Okay, so we need to show that for all G and G, n in n, G and G inverse is in n, right? That's what it means to be normal. Okay. Well, G is an internal direct product of H and K. So we can write, you know, or maybe let's say fixed G and N. G and G and N in N. And since G is the internal direct product of H and K, we can write it as H times K, right? And write G equals HK for H and H and K and K. Okay, so now let's do the conjugation by G. G and G inverse is going to be what? So it's going to be HKN, HK inverse, oops, inverse on the outside, which is HK N K inverse H inverse, right? Okay, now, again, important thing, remember we proved that H and K commute with each other, right? So in particular, I can move them around and it's not an issue. So what I'm going to do is I'm actually going to try and move it so that the H's, because what do I know? I know that N is normal in H, right? I don't know anything about how N is related to K, but I do know it's related in H. So what I want is those H's to end up beside the N's, right? So let me manipulate it so that that's true. So I'm going to get K, H, N, H inverse, K inverse, right? Now, right now, that's the best that I can do because I can't push the H's through the N's. I don't know that that's true, right? I don't know that I can, like, you know, that N might commute with things in H. That doesn't need to be true. So right now, this is the best that I can do. However, now I can use the fact that N is normal, right? So what that means is that H and H inverse is in N. Right? And N is itself a subgroup of G. Or sorry, of H. Okay, so that whole thing is actually in H. And again, H and K commute with each other. So now, in fact, I can take that K, right? Like maybe let me put brackets around this. So we're kind of thinking that as one element. That thing is in H. H commutes with K. So now I can take that K and I can push it through to the other side now. Right? These two things are going to cancel each other out, the K and the K inverse. That's just going to give me H and H inverse. And again, I know that's in N because N is normal in H. And so now it's normal in G as well. As wanted. So basically, again, it's this idea that, you know, if we think about this, again, being isomorphic to the external direct product, the H's and the K's shouldn't interact with each other. And we can see exactly that happening here because we were able to just filter through the K's so that they were all on their own, did their own thing, and canceled each other out. So the only thing that was actually relevant and important here was the normality of N in H. right? Because we were able to get rid of the K's and say the K's really don't affect this whatsoever. In fact, it tells us something else, which is cool, that if we conjugate by G, right, the only thing which matters in that conjugation is the component H itself, right? We don't care about what the K is. We only care about what the H element is, because the K's will just vanish and disappear. So that's kind of a cool thing as well that we can learn with our internal direct product. Okay, any questions about that? No, it's okay. Okay, so let's go to the worksheet then. That's basically what I wanted to do. Let's go to the worksheet. So I'm going to give you a second to pull it up. And I also need to pull it up. Where the hell is it? There it is. Okay, let's see. We might as well do all three. I think we've got time. Well, do we got time? Well, definitely let's do 1 and 2, and then we can argue about 3. In fact, actually, let's do 2 together right now. Okay, let's just skip straight to 2, because maybe we could do it really, really quickly as a class. Okay, so this is the worksheet now. And so now we're really going to say, you know, I guess when I say let's do it quickly together as a class, I'm really banking on whether or not you see what it is you're supposed to do. So if we go straight to question 2, it says the following. So just in case, you know, you're too lazy and you didn't pull it up. So we've got the G is equal to Z. Okay, so we're taking the integers. We're taking H to be the subgroup generated by 7 and K to be the subgroup generated by 5. Okay. The question is, show that G is equal to HK. Is G equal to H cross K, right? So show G is equal to HK is G equal to H cross K. Okay. Now, we actually did this question much earlier in the year when we were first talking about, you know, subgroups generated by an element. We said, look at the integers and figure out what is the subgroup generated by 2 elements. Does anyone remember this one? So let's maybe say as an aside here, if M and N are integers, then the subgroup generated by M and N is equal to what in Z? Does anyone remember what that was? We definitely did this in this lecture when we were talking about these subgroups. Does anyone remember what this one is? Because if you remember this part is easy. Do you have any guesses what it could be? Even if you don't remember it, do you have a guess of what it might be? Not even a guess? Yeah, exactly. No, okay. No, but your words are more or less right. The first word maybe is related, obviously, right? But exactly, it's the GCD of M and N. Right? And the proof of this really isn't too bad. So proving, for example, I mean, it basically comes down to Beziewicz lemma. Maybe when I write this, some of you will be like, oh yeah, right? So remember, the GCD of M and N can always be written, right? Beziewicz lemma says, given M and N, you can always write the GCD as a linear combination of those elements, right? So we know that we can write the GCD of M and N as MR plus, you know, NS for some R and S, right? And that precisely shows that the GCD is a subset of the, right? Like MR plus NS is precisely what the elements in the subgroup generated by MN are, right? Okay, and then the other direction is automatic, right? Because it's the greatest common divisor, certainly M must be M is a multiple of the GCD. So the opposite directions are true immediately, right? Is immediately true. Okay, so just convince yourself that it's true. Right? Or what you could say is, again, everything in the subgroup generated by M and N looks like MR plus NS for some R and S, right? And so in particular, since the GCD is the least common multiple of both of those things, all you have to do is scale the GCD to get anything that you want, right? So the other direction is immediately true. Okay, so this shows, therefore, oh, I guess this is the product though. I guess we're not taking the subgroup generated by both of them. So maybe this isn't a relevant conversation. No, but it effectively is, right? Because that's basically what we're doing when we do HK. So if we take something like 5 plus 7, right? That's what we're doing here. We're saying, oh, everything in the thing on the 5 side looks like 5M, and everything in the right-hand side looks like 7N, right? So this is going to be precisely this set. And yeah, we know that there's some combination of these things that is equal to 1, right? Again, because they're coprime, right? So 5 and 7 are coprime. In fact, we could just write one of them down, right? It's 3 times 5 minus 2 times 7 is equal to 1. And so now every number can be written in that form, right? And so we're done. 3 times 5 minus 2 times 7 is equal to 1. So 5 plus 7 is all of Z, right? It's certainly a subset. 5 plus 7 is a subset of Z. And if you give me any number Z, just take this equation here, multiply it by that number, and now you've shown it's in the left-hand side as well, right? So in this case, because it is abelian, they work out to be the same thing. Okay, now, what do we need for G to be the internal direct product? Is this the internal direct product? Namely, if I take a look at H and I take a look at K, is their intersection trivial? Can anyone tell me something in their intersection that is other than 0? And if you can't, prove it to me. 35, exactly. 35 is in 7 intersect 5, right? i.e. 7 and 5, the intersection of these two things are going to be precisely all of the multiples of 7 and 5, right? Or rather the numbers that are divisible by both 7 and 5. So the smallest such number is, smallest such positive number is 35. The intersection is definitely not trivial, so it's not an internal direct sum, right? So G is not H times K. Okay. All right, so that was question 2, which is nice because we kind of did it as a class. Now let's pivot into 3. So 3 is basically saying, is it like maybe 5 and 7 was a bad choice? Is it ever possible to write Z as an internal product of two groups, right? So for question 3, it says G is equal to Z. Are there non-trivial subgroups? H and K such that Z is equal to the internal product of H and K. Okay, and what I want you to think about is exactly the example that we just did, like what went wrong. Certainly, you can find two groups whose product is all of Z. That's not the issue, right? Probably the issue is going to be their intersection. So is it possible for me to ever take two subgroups and ever have them have empty intersection? That's really what this question is saying, right? Is it possible to take two subgroups of Z and have them have finite intersection? Or sorry, non-trivial intersection. Okay, so give that a shot and tell me what you think. Again, I'm going to give you, let's say, 3 or 4 minutes to work this out, and then we'll come back and we'll talk about it. Okay. Anyone have an idea? Okay, because the idea is exactly to do what question 2 was, right? No idea? Okay. Right, it is false. And yeah, exactly. And the question is, what could go wrong? So here, let me set it up. So basically, suppose that well, let's just take any two subgroups, H and K, right? So solution, if H and K are subgroups of Z, right? And normal because Z is abelian. Z is cyclic, right? And every subgroup of a cyclic group is cyclic. Then they are cyclic. So H is generated by M and K is generated by N for some M and N. Right? And now we're in the exact same situation as above, right? Where we had, can Z possibly be an internal direct product of M and N? Namely, let's suppose M and N even end up being co-prime. We're not really worried about that. Whatever M and N are, is there something in their intersection that is not 0? So can somebody give me something in H intersect K, which is not the number 0? Right, exactly. But note, not boot, that's not but, note that M times N is always going to be an H intersect K, right? Exactly, yeah, Harvin, yeah, exactly. So what this says, right, is that no matter if you give me two non-trivial subgroups, M times N will always be in their intersection, which means it's impossible for you to give me non-trivial subgroups whose intersection is trivial, right? Thus, it is impossible to give two non-trivial subgroups with trivial intersection. And if that's just not even possible, then it's certainly not going to be possible to write anything as an internal direct product, right? With trivial intersection. Thus, it's impossible. If you wanted to as well, you totally could have done this like by contradiction, right? Suppose that Z was H times K. Let H be the subgroup generated by M. Let K be the subgroup generated by N. Oh, note that there is something in its intersection, but that's not possible. So we must have had a contradiction, right? So if you want to do it like that instead and say, do it by contradiction, you totally can. But I think this is a totally fair thing to do as well, which is say, look, no matter what two non-trivial subgroups you give me, there's always something non-trivial in the intersection. So it's impossible to write this as a internal direct product, right? There was just no chance that we could have done it as well. We just can't find two groups that have trivial intersection, right? So that's kind of nice. And again, like in some sense, that's obvious because if you think about what any of these subgroups of Z look like, they basically just look like the multiples of a number, right? And if you give me any two numbers, eventually they overlap because they have to kind of shoot off to infinity, right? They can't like cyclically come back and just keep missing each other. That's not possible in Z. So that's the moral reason why this fails, right? So this is also kind of interesting though, right? It says not every subgroup can be written as a non-trivial internal direct product. And in fact, even one of the easiest groups that we have to work with, Z, which sure, it's infinite, but it's cyclic, right? It's cyclic and abelian. So it's a very nice group, but we kind of immediately fail to be able to write it as an internal direct product of any of its subgroups. So, internal direct products can be useful, but they're not like universal, right? We can't always utilize them in order to study the structure of what we want to do versus the example, let me scroll up here, versus our example here where we got, where did I do D6? Where the hell is it? There it is. Versus this example, D6, which was isomorphic. So again, right now we know, maybe just let me kind of put this in here now that we know it. We know now that D6 is actually isomorphic to the external direct product of Z2 and S3. Right? Because we proved that internal direct products are isomorphic to external direct products, which means knowing that D6 was isomorphic to S2 cross S3 as an internal direct product also gives it to us as an external direct product. And this is really cool, right? You can imagine we can use Z2 plus S3 to really study D6. Like I've got some sort of grasp of how to think about this from a different perspective. And maybe I can use that in order to figure out some of the structure of Z6. That's really, really cool. Unfortunately, it doesn't, there's nothing that we can do for Z. But I mean, like we could do it for Z6, right? Like the very previous example was precisely that Z6 was Z2 plus Z3. So sometimes it works, sometimes it doesn't. And, there's only so much that we can do about that, right? It's not a guaranteed thing. Okay, so that's kind of a nice example there. The last question, which I think is frankly the hardest, is question 1. So let's try that and then we're done. But let's give that a shot. So question 1. Okay, so suppose that the index of G over its center is a prime squared. Right? Show that G mod ZG is ZP cross ZP. Okay, and let me do a little recollection here. So this one's in the book, but I didn't talk about it here. So recall, if the order of G is equal to P squared, then G is equal to Z P squared, or G, I should say isomorphic to ZP plus ZP. Okay, so this is something that was done in the notes in and around this section, which was if G is isomorphic, or if the order of G is a prime squared, then it's exactly one of these two groups. It doesn't have a choice. It's either ZP squared or it's ZP plus ZP. Okay, so that's important because in this problem, you're told that the index of G over ZG is P squared, right? So immediately we're going to be able to conclude something about that. So I'm going to give you 4 minutes here. Let's see what we can come up with. If you get stuck, maybe think about Theorem 7.16 in the notes. That big hint might help you. But yeah, 4 minutes, let's give that a shot. Theorem 7.16 might be what to look at. Okay, any luck with this one? What do we do? What do we get? Okay. Well, if you're typing, just keep typing. So we're told about the index, right? And the index is the same thing as the order of the quotient. We know that the center is normal in G as well. So we can take the quotient and that's not an issue. So we know that the order of G mod Z of G, that by definition is the index of the center in G, right? That's equal to P squared. So by the result that I put there in yellow, this group G mod ZG is either ZP squared or ZP plus ZP. So either G mod ZG is isomorphic to Z mod P squared, or G mod ZG is ZP plus ZP. Now, we want to prove that the right-hand thing has to be true. So somehow we need to prove that the left thing can't happen, right? And the big hint here was Theorem 7.16. So theorem 716 says, maybe let me kind of put this in yellow here. If H is a subgroup of the center and G mod H is cyclic, G is abelian. Right? Okay, so what that means is if G mod its center was isomorphic to ZP squared, that's cyclic, right? That's cyclic, so that implies G is abelian. Right? But if G is abelian, its center is everything, right? That's what it means to be abelian, is that your center is everything. And in that case, what does that mean? So thus, because we're told that the index of ZG and G is P squared. So the index of G of Z of G and G is equal to 1. And that's a contradiction. 1's not prime. So thus, it has to be the second one. And we're done. Okay, anyway, it'd be like, that would imply that E is isomorphic to that group, which can't be true. Yeah, so I mean, technically we didn't say it couldn't be the trivial group, but basically the trivial, we're gonna say that the trivial group does not have order prime squared, right? So you're right, exactly. That would say if G was equal to Z of G, then their quotient would be the trivial group. And we're saying that, I mean, that in theory could happen, right? Anytime you take an abelian group quotient by the center, you do get the trivial group. The reason why that's a contradiction, we're throwing it out, is the trivial group does not have order P squared, right? Because P is not a prime, right? Or sorry, 1 is not a prime. So that's just not allowed to happen for that reason. Okay. Okay, so any other questions about that? Does that make sense? Cool, cool, cool. Anyway, everyone, that takes care of it. We are completely and totally done. So is this answer similar to the proof for 817? Let me just take a look at that. What is 817? Is that exercise 817 or is there an example 817? Oh, so this uses, because you might say, like, what does this have to do with internal direct products? It uses 817, which is an internal direct product proof, right? So we really leverage 817 in order to be able to do this. Which is how it's actually related to the internal direct product. Otherwise, you can see there's no internal direct products around here. The proof is different though, right? In the proof of 817, you basically say, look, it's cyclic, or if it's not cyclic, then you choose two elements of order P, right? And that here's an element of order P, choose an element of order P that is not in the subgroup generated by this thing. And look, those two have to generate the entire group. And that's basically how the proof of 817 goes. Right? So it's a little bit different. Okay, anything else? We're okay. All right. In that case, everyone, this is it. I'm going to hang out for office hours after this, but otherwise, that is our last lecture. It is basically our last meeting of the year. The exam is like December 20th, something terrible like that. Aaliyah's posted, when our office hours are, heading into the examination. So check those out if you have any questions. Drop in for that. Otherwise, thank you everyone for coming. Attendance hasn't been great in this lecture all year. But for those of you who did come, you provided me with some sense of validation. So that's very nice of you. But other than that, I hope you had a good time. I enjoyed teaching you. And thank you everyone for a really solid semester. I enjoyed it. Good luck on your examinations. And I'll see you around. Thank you. Thank you.